Hey guys, welcome back to a new Scrap Mechanic video. Today, we're not actually going to be focusing on Scrap Mechanic today. We're going to be focusing more on how CPUs work. Now, if you've been watching some of my Scrap Mechanic videos, you know I'm pretty into logic and stuff and computers and stuff, and I've actually been making a actually fully working CPU and computer inside of Scrap Mechanic using logic blocks. So if you want to check that out, then please do. Probably give a link in the description. I'm probably going to forget that, so just look in my channel and you'll probably see that. It's probably a few episodes ago. But yeah, I've been working on CPUs and stuff, but if you guys don't actually know what a CPU is, many people don't really know what a CPU is, even though they have them inside of their devices that they're watching these videos on, then they're probably going to need to know what that is before they can watch my videos, because I talk about CPUs quite a lot and talk about all the things that actually work inside of CPUs. This video's gonna be kind of basic. Much of the terminology might not be the exact terminology. I'm obviously not an expert at CPUs and technology and that, but I know most of the basics of how things work, and I'm going to be showing you guys how the basic principles of how a CPU works in real life and also in Scrap Mechanic. As you can see, I've actually built real working parts of a CPU of part of my actual computer build inside of Scrap Mechanic. But I'm going to be showing you guys how an actual CPU works in real life as well. So, CPU stands for Central Processing Unit. If you've never looked inside of your computer before, or you've never really seen a CPU on the internet before, then basically it's just this flat piece, square part that goes inside of your computer, and it's right in the middle of your motherboard, which is the massive board inside of your computer. It's usually covered up by a cooling unit, or some sort of liquid cooling unit where it can be cooled down, because obviously these things get quite hot, as the CPU is kind of referred as the brain of the computer. The CPU does all the different calculations, does everything that the computer needs to do as it runs. Now obviously, if you're pretty good at computers, you know there's a other processing unit that's called the GPU. That's more for graphics, and I'm not going to be covering that in this video, and there's also kind of similar to the CPU, but the CPU is kind of the main thing. The graphics processing unit is kind of a different thing that's focused more on graphics and actual processing. And yeah, if you know what a CPU is, you can probably work out what a graphics processing unit is as well. Now, the central processing unit is basically what does everything of the computer. Everything else, the part that stores stuff or does other things, and the CPU is basically what does everything. It's basically the sort of brain area, actually takes the information and actually does something with it instead of just storing it. So we're going to be looking inside of the CPU. I've picked Scrap Mechanic to represent this video, as it's pretty easy to make some visual representations with Scrap Mechanic. And also you can make these really cool blocks here where I take the lid off the CPU. So inside the CPU here I've built, there's 4 different compartments, or squares or different sections to the CPU. These are the 4 main areas that you need to know for a CPU to actually run. This is the really basic version of a CPU, by the way. This is a really basic. In a modern CPU, there's many different layers of this stuff. There's so many different parts to a CPU, but basically it all comes down to these 4 different parts. So the first part is I/O. If you don't know what that stands for, it stands for input output. So this is basically sort of like a portal to the outside world. Now the CPU is kind of contained inside of itself. It has everything it needs to run by itself, but I/O, it basically allows it to socialize with the outside world. So this allows it to contact hard drives, allow it to output to monitors and different stuff, allow it to take inputs from keyboards and that. So if you're wondering how it can actually control stuff, the I/O is kind of how the CPU talks to different components on the computer. So the I/O is not really a big part of the CPU, it just allows it to talk. The CPU can still run without the I/O, but you won't actually have any user input or any sort of output that's coming out, so you don't actually know what the CPU is doing unless you have I/O, which allows you to take outputs and stuff from the actual CPU. So it's not really the biggest part of the CPU. But we can move on to the control unit. Now this is one of the main parts of the CPU. The I/O and cache you don't really need too much. But the control unit, this basically sorts information coming in. So basically any data traffic that's coming in, the control unit basically controls all the data. Like it says in the name, it controls all the data, sends it to the necessary areas, controls memory as well, so also like controls memory, puts it in cache, takes other memory from like the hard drives through and controls the inputs and outputs as well. Down here as you can see it's connected to the input and output. So this basically controls everything that's coming into the CPU and everything that's going out, and also controls all the memory and stuff like that. But this also controls the instructions, and the instructions are basically telling the CPU what to do. So basically the control unit takes instruction in. If it deems the instruction that it needs to be calculated or do some sort of operation on two numbers, then it would send it to the ALU. Now the ALU stands for the Arithmetic Logic Unit. Now hence the name, it's basically the part which does all the calculations. So this is where all the mathematical functions come in and all the different comparison operators come in. So this basically adds two numbers together, it takes away two numbers together, it can divide two numbers, it can multiply numbers together, it can also compare numbers, so you can see if they're equal, less than, or greater than as well. So the ALU does all the calculations, and then it sends it back to the control unit, where this sends the information back to where it needs to go, i.e. cache or I/O. Now cache, what cache is, it's a form of memory. Now you probably heard of memory in like hard drives or SSDs. But the memory in hard drives or SSDs are usually high capacity, so you might have been hearing words like gigabytes or even terabytes of data. But hard drives are not actually inside of the CPU. The hard drives are like an external piece of hardware that can be connected up in through I/O here. So the CPU can contact hard drives, but they're really slow. Hard drives are really slow compared to CPUs. CPUs run about usually today is about 3 to 5 billion times a second. So hard drives are way too slow for the control unit to actually take information in at a fast enough rate. So they have a thing called cache. Now cache doesn't really store that much information. Unlike hard drives, it can only store about 3 to like 10 megabytes of data, not that much compared to like the gigabytes that hard drives can store. But unlike hard drives as well, it's really fast memory. So basically, the reason it's right next to the control unit is because it needs to take memory in and process that really fast, about a few billion times a second. And yeah, hard drives can't really do it that fast, so they're going to need cache, which basically allows them to take information in. Now obviously, because it's such low capacity, they're going to run out of space soon. So any data that's not currently being used in cache gets sent back to the hard drive. Now because the hard drive is quite slow, it will take a while to process that, but that can be used for more data coming into the cache. And it kind of regulates itself because the cache is really fast. Once it's finished, it sends data to the hard drive where it can be stored long term. Cache is kind of like a short term temporary memory area. And the cache actually doesn't store information in like when the computer's turned off. So once the computer's turned off, like this data gets removed. Hard drive is kind of like the long-term storage where like everything's put away for like long-term. Cache is where actually the data needs to be used. So like if you start like a Word document, loads of different like applications and layouts and stuff will be stored in cache because the control unit needs to take that information in really fast, and like all the different stuff needs to be stored in the hard drive. So cache is actually really useful. If you don't have much cache, then the control unit will back up, and that will potentially slow down your CPU, which is not a good thing, because obviously you want to make these things as fast as possible. So this is kind of like the basic rundown of all these different parts. I'm going to be moving on to these more like complex breakdowns of each different part here, as you can see on the board. Okay, so moving on over to the Arithmetic Logic Unit, which is the ALU here. That's the green part of the CPU. As you can see, I've kind of scaled it up here so I can see what you guys can see. As you can see, this is a bit more complex than the other diagram I have shown here, but it will make sense once I start explaining it. So over here I have an actual real working model of an ALU which I've been building for a computer design I've been working on. So as you can see, there's quite a lot of connections and stuff with logic gates, and yeah, it has all the different comparison stuff in that. And it different has like, it can add at the minute but can't subtract. I'm still working on this part, but as you can see, this is a kind of like a actual working version. I'm going to be showing you guys like the simple basic thing what I've done here. So at the start, once information comes into the ALU, there's these two different blue sections here. Now these blue sections are registers. Now I've labelled all the registers in blues here so you can see them clearly. So registers are kind of like cache, but cache has got like multiple different bytes of memory. Registers is only 1 byte of memory. Now if you don't know what a byte is, it's basically like a 8-bit binary digit. Now if you don't know what binary is, then look up a video or watch one of my videos on how binary works. But for now, if you don't know what binary is, just refer it to like a number or a letter. So one letter or one number can be stored in one of these registers at one time. So as you can see, there's 2 registers here. So the ALU takes information from the control unit over here. So let's say an instruction comes through for it to do an addition. So 2 numbers coming in to do an addition, as you can see. Comes in, stores 1 number in this register here. Let's call this register 1. Another number comes in, and this gets stored to register 2. So now we have 2 numbers here. These 2 numbers get fed into this kind of like calculation section here. So we have 4 different sections here. Actually 5, including this area. But we have 4 main operators here. So we have the addition, subtraction, multiplication, division. So these are like the main operators that everyone knows and like knows what they are. And up here we also have the comparison unit. You might not think to have a comparison unit, but what this does, it basically tells you if the numbers are equal, greater than each other, or less than each other, like symboled by these like crocodile symbols here. Also it can tell you if they're not equal, but obviously you can just take the inverse of this thing here. Now, when the 2 numbers come in, the control unit selects which operation it needs to do. So let's say it wants to add the 2 numbers together. These 2 numbers get fed in until they reach the addition unit, and these numbers get added together. So this is what an addition unit looks like. This is an actual adder that I've made. This is a binary adder. It's currently not connected because I'm still working on it. So let's say the 2 numbers get added together. They get sent back through here, and they get sent to this output wire that gets sent back to the control unit and does whatever calculation it wants. Now let's say the control unit actually wants to compare 2 numbers together. So the 2 numbers come here, get stored in this first register here. Second number comes into the second register here, which gets stored. These 2 numbers are now stored, so it doesn't require any more input from the control unit here. It can now do what it needs to do on its own. So now these 2 numbers go through here, go up here, and actually feed into this comparison unit because it wants to see whether number 1 is bigger than number 2. So it's going to pick this option here. Now it's going to do some comparison. As you can see, this is my comparison unit. Basically checks which one is bigger and then outputs to these 2. So it checks whether it's bigger or not. If it's not, then it will represent as the less than. If it is, then it will go as greater than. And then these 3 here, plus the inverse of the equal one, so if it's not equal, go into these 4 flags. Now flags are basically different, like a boolean line, which goes to the control unit directly, telling it whether 2 numbers are the same, or if they're not the same. So these are only like true or false lines. They don't have to have like the binary digits going through. So obviously this output is going to contain multiple wires. So if you send through an 8-bit line, then the output's going to be 8-bit as well. So it's going to have to go through a bus. Now a bus is basically multiple wires together that go through like a long line. So it's basically like kind of like a highway of data going through. So if you want to so basically flags are basically an easy way to communicate with the control unit if like two numbers are the same without having to send them through the same output here. So as you can see, this is the comparison unit, compares two numbers. These are different operators here. These add two numbers. Really simple this. Stores two numbers in these registers here. Does the calculation, sends it back to the control unit. So that's the ALU here. Really simple. Now if you understand it, it's pretty simple. Only a few things here. It's probably going to be like the easiest thing to build, to be honest, out of all these three things. So yeah, the ALU is probably the most simplest out of all these. I'm going to move on to the control unit now. So as you can see, I'm going to open up the control unit. But before we do that, we're going to be looking at this. Now this is an instruction. This is going to represent instructions and lines of code. Let's say each black line is a line of code. Obviously, if you didn't know, computers run code in a language called binary. It's basically where there's only two different possible outcomes for each bit. So it's either black or white. So let's say this is the first instruction, this is the second piece of instruction data or whatever. As you can see, these are different lines of code. So each black line or different like piece of information is the line of code. Now, as the line of code goes down, you can see these different like markings on the side I've made. So the pink marking, this is the instruction line. So the first line out of each program here, or each line of code, is going to be the instruction line. Now the instruction line basically tells the control unit what to do. The lines after it, which are marked in white here, are connected to the instruction line. Now the instruction line is going to require some pieces of data. Some instructions don't need any data, which they can just move on to the next instruction instantly. But if you're doing addition, obviously you need two numbers to do addition, so it's going to require two different pieces of data. So as you can see, there's two lines here. So let's say this function is addition, and then we have two pieces of data here. Let's say these are the two numbers that need to be added together. Now these numbers will be added together and they'll be stored inside of the control unit. They won't have anything done to them. This second instruction, this could be like the output instruction. So there's only one piece of data linked to this instruction, which is the address. So once you're outputting data, you need an address, because if you don't know where you're actually outputting the data to, then you're probably just chucking it out to like some sort of hacker that just like takes your data in and stuff. So this address is basically a kind of ID for each piece of hardware outside of the CPU. So let's say you have a monitor plugged in, maybe you have like two monitors plugged in. The CPU needs to know whether you want to pick the first monitor or the second monitor to output the information. So let's pick an address, like address number 1. It will output the information from this calculation here, and then go through all the different instructions down here through the entire piece of code. Obviously in real life this is going to be like gigabytes long, going down through all the different instructions, telling the control unit what to do. So now if we actually open this thing up, it gets a bit more difficult than the arithmetic logic unit, but trust me, I'm going to tell you what actually happens. So as I told you, the first line is the instruction. Let's say we're going through all the different lines of code. The first line of code comes through this line of wires here. Now these like lines of wires and stuff here are called buses. Like I said before, these are just like multiple lines together that just run through the different circuit. Now this bus leads up to this register here. As you can see by the blue, I've labeled it. It's a register. Now this register is an instruction register. It's called an instruction register because it stores the instruction. Now, like I said, the instruction is marked by this pink number here. This is the first line of code to come in. So this code comes in, it sees that the instruction register is empty, and then fills up the instruction register. So the instruction is now stored. The control unit knows now what to do. It's just waiting on the pieces of data. So let's say the first line of code is an addition instruction. So the control unit wants to add something together. Obviously it doesn't have numbers now, but more numbers are coming in now. So the second and third pieces of data are coming through the bus. So let's say this bus and this bus are connected to the I/O ports, which are connected to the hard drive. So this is pulling data from the hard drive. So let's say like these instructions are coming in from the hard drive here. So the two pieces of data coming through, let's say one piece of data is coming through, it'll check to see whether the instruction register is filled up. If it's not, obviously it'll fill it up again, but if it is, then it'll go over around here, up through here, and get stored into here. Now obviously there'll be a few more registers inside of here which will be storing pieces of data, but I haven't represented here. All this stuff in the middle, by the way, don't actually look at this, it doesn't really matter. I'm just trying to make it look a bit more complicated and stuff. That just kind of shows you like all the different sorting and stuff going in there. But yeah, so basically it gets stored in there. The second piece of data comes in, goes checks whether the instruction is actually full or not. It sees that it is full, so it needs to count as a piece of data. Goes around here, goes back up into here. Now the control unit realizes that it is now capable of doing a calculation, so it halts any instructions coming in further. It then sends an information to the ALU. As you can see, this green arrow represents the data going in from the ALU. You can see the flags coming in here and also the data going in. So it will send those two numbers over to the ALU. Also, it will tell it to add those two numbers together and then bring back the data. So it will go into the ALU over here. Two numbers will come through, being stored into these two registers here. It'll be told to add, which means it'll do the addition, and then it will send back the data through this wire here. Then this wire will come all the way back up, go back into here, and it'll be stored into some sort of output register. Now, usually a control unit has a few different registers just to store numbers in. So it'll usually have like one register in it. So once a calculation is done, it'll bring back a number and be stored into an output register. This is just a temporary register. Basically it's just the storage value that's inside of it, so it just stores any value that has been outputted from the ALU. The next instruction is an output instruction. So as you can see, this instruction register has now been cleared up because instruction's already been completed. It'll come in, be stored into the instruction to output the piece of information. Now, it's still waiting on a piece of data because obviously you can't output to anything. So the data comes through this line, checks to see if the instruction register is available, sees that it's already full, goes all the way around here into the control unit. That piece of data was the address. Now, this control unit will now take that output from the ALU, so the output register will now be taken out and it will be thrown into the data bus over into the I/O bus. Now, the I/O will be sent to some sort of address. Now, the address you got put in will send it to a specific device with that address. So you can have any device with any sort of address that you want to have. So usually you'll have to output it to some sort of display. So if you want to output to like a binary display or something, you can, or a decimal display, you can. But the reason for an address is because if you have multiple different outputs, then you might want to like label them with multiple different addresses so you know which one you're actually sending the information to instead of like any of them. So yeah, so that's the simple way of how a control unit actually works. And also there's one more thing that's left. This control unit can actually save data to cache. Now, I told you about cache earlier. It's basically temporary storage for the control unit to store information. So let's say this says to actually store the information from the ALU to the cache. So maybe it wants to be storing that information for a later calculation, then it can. So it will take that information from the output register here, it will throw it into these like 6 different wires over here, and they'll be sent over to the cache, which I'll now be going over to now. Now, this is the cache. So as you can see, it says cache up top here. This is the like really fast storage technique. So as you can see, by what I've created here, there's loads of different cells. So these square blocks represent cells. Now each one of these cells can store about 1 byte of information. As you can see, there's quite a lot of them, but like relative to what we have like in the today, we have like a few megabytes. This is not that many cells of data. But cache is not supposed to be high capacity, it's supposed to be high speed to contact with the control unit. So let's say the control unit wants to write a piece of information to a specific cell, this is going to be the address bar. Now this address bar will never change, it will never turn to a different sort of like different thing. You'll send an address in, let's say this is a different type of register, this will just store a piece of information in here, so this is the address. Now as you can see there's two different wires, or buses if you want to say that, and the first one's obviously the address one. That basically tells you which cell to look for. So each one of these cells is labelled with their different ID, so you know which one you're accessing at one point. So obviously you don't like save the same number in like 10 different cells. So let's say each cell has a number like incrementing every time. So this is cell 0, 1, 2, 3, 4, 5, and so on over 3. So if we want to access cell 1, then we'll put the address to 1 in this register, and then we'll be looking at this cell here. So let me just highlight this cell. So let's say we want to write a piece of information. Let's say we want to write the number 2 to this cell. Now this wire here, which comes in handy, this wire tells the cache whether you want to read or write. Now the difference between reading and write is if you read a piece of information from the cache, that means you're taking information outside the cache and using it for a different purpose. If you're writing a piece of data to cache, that means you're actually setting data to a specific cell on the cache. So you're actually like saving a piece of data, that thing. So let's say we want to write to the cache. Now we'll set this to either 1 or 0, which represents saving or writing to the cache. So we'll set that to write mode. Now write mode allows you to input another piece of data from here. Now this bus can be input or output. So if it's set to write mode, you can input a piece of data. If it's set to read mode, then it can output a specific data from a specific cell. So this has got like a multi-purpose I/O line that connects up to the control unit. This line doesn't change; it's still the address line here. But if we're writing to a piece of data, this line comes in handy. As you see, it's marked in red. This is because this is the set line. Now the set line, basically if you're writing a piece of information to the thing, you'll pick an address, you'll pick a number to save to that specific cell in the cache, and then you'll tell this red line to set that information in stone. So that basically just like confirms the save, and then this information gets saved here. So basically we can change the address as much as we want, but it won't actually save anything until we actually use this line here, which sets it permanently. Let's say we want to read that information back, so we set the address here, we set it to read mode now, and then basically we don't do anything with this line. It goes to that address. So let's go to address 1 again. As you can see, it's marked as blue for this different purpose, and then it'll send this information outside of this output bar. We don't need to use a set line because all we're doing is reading. We're not setting any information inside the cache, so we're actually reading information. Same if we want to set the information to, let me say, like cell number 3. I think this is cell number 3. Yeah, this is cell number 3, because we always start at 0, because obviously it would be wasting ID if we didn't actually set this one to 0. Cell number 3 would be this one, so let's see, this is cell number 3. We want to write a piece of information to this, so we set it to write mode. We input the number we want, so let's say red is like the number. Obviously red's not a number, it's just to represent what we're saving it to. And then we use this set line to confirm the thing. If we don't use the set line and we change the address, maybe to like another one up, it won't actually set that information. It will just go back to its original position. But if we use the set line, it will set that in stone, and we can move to a different address, and that will stay the same. Now, obviously, if you want to remove this piece of data, then you can just set the number to 0 or its original position, or idle position, or null position, whatever you want to call it. But you can also add like a different wire, which is like a reset wire, which like resets that specific cell to its original position, instead of like using 0, but like it really doesn't matter. You don't really need a reset line. So this is how cache works. Really, like a really simple storage system. As you can see over here, this is an actual real working cache, similar to this one, but it's kind of different. Instead of having 2 buses here, we have 3. and it removes the read write line, so we can actually read and write at the same time. So we can still read information and write at the same time. Doesn't really matter, to be honest. As you can see, this bottom one is the address bar. This top one is the input one, so this is where we input numbers to save to. This is the output bar, so the blue one's output. Currently, I've only wired up 5 because I can't really be bothered to wire up all these at the minute, and it's going to take a long while. As you can see, it's really complicated and I don't want to mess up, so I'm going to do that later. But as you can see, we've got 5 registers intact. Let's say we want to access register 1. So as you can see, by this logic gate here, you can see register 0 is currently activated. So if we pick register 1, that's 1 in binary, by the way, we've selected this register. So once we've selected this register, we want to type in the binary value of 5. So now, you realise that this is 5. Now, number 1 is currently set to 3, because I've already been testing this. Register 1 is already set to 3. You might think, oh, that must be saved to 5 now, let's move on to register 2 now. If we go back to register 1, it's still 3. The reason it's still 3 is because we haven't used the set line yet. If we press set, that will reset that line to 5 now, and then we can move on to a separate piece of data, change the number up, set that as that. If we go back to number 1, as you can see, it's still saved that data, and everything's working perfectly. Everything's working good. As you can see, it's all good. And we can erase the data by just setting the value by 0 and then going through each different register like this. As you can see, each register is empty at the minute, so we've cleared everything, and that's basically a simple way of how cache works. Obviously, in real life there's going to be many more cells, and because you can have smaller parts in real life, and in Scrap Mechanic you can only have these logic gates. But yeah, this is kind of a visualization of how a CPU actually works. This is a really basic CPU. Now I'm actually modelling my Scrap Mechanic CPU after this, so that does prove that you can still use this architecture to actually make a CPU. It can still function, but it's a very basic one. It's not the most efficient version also, and it's not really modern, obviously, because modern computers would have multi-cores, which means it has multiple control unit, has multiple ALUs, and has a lot more cache than this in separate versions of cache as well. So yeah, there's a lot more complex CPUs out there. This is a really basic one, so don't think this is how exactly your computer works, because this is like a basic representation of how it'd go about doing this process. Now, I'm not an expert, so if there's any facts in this video that you thought not correct, or you want to correct me or anything, put a message down below, and then I'll probably make a pin message that will get any facts correct as well. But if this did help you out in understanding how your computer actually works, then please hit that likes and subscribe button. My Fortnite video actually did insanely well in the past month or so. It's got around 20,000 views. Now 20,000 views is about 5 times as many views as my entire channel's videos combined. And also I've gained about 100 subscribers off that video as well. So a huge thank you to you guys that was through that Fortnite video. It got a huge amount of support. It got about 500 likes on it. Hopefully, if you guys are still watching this, then make sure you're subscribing to see more content, explaining how all these different logic stuff is working. Also, we'll be seeing more Fortnite content if you really want to see that as well. But for now, that's about it for this video. Make sure your post notifications are on it as well, so you can get to see my next video as soon as it comes out. And yeah, goodbye.